Awesome. Yeah, thank you so much, Helen, and to the organizers for inviting me here. It was very nice to drive up here and so much less stressful than traveling across the Atlantic to a meeting. Really nice. So this is a talk that's basically a little bit about altimetry, but also kind of morphing into talking about a paper that came out earlier this year, which was a review paper. And then looking into the future, I want to tell you guys all about a new mission that we're proposing to NASA. We've just submitted it. It's called EDGE, and I want to tell you all about that and get you excited about that because there's maybe not many missions coming in the future, and this one is one that we might get. So I want to make sure that you all know about that. This is the Science special issue that came out. Unfortunately, the timing of this was pretty terrible in respect to, you know, local, sort of global events or country events. It came out in February 2025. Everyone was a bit distracted. But maybe you've seen it, maybe you haven't seen it, but if not, it was actually a whole special issue. And I don't know why they use this AI cover. It was kind of not really very great. But anyway, there's also a review by Julian Strover et al. About the Arctic, which is really, really nice as well. And there was another one about diversity, marine freshwater biodiversity in the Antarctic as well. But our paper was called Antarctica in 2025, Drivers of Deep Uncertainty in Projected Ice Loss. And so I'm going to tell you a little bit about this paper. I've been told by a few people that it's been very helpful for teaching, actually. So if you're interested in teaching about glaciology in Antarctica, we kind of like went through the system piece by piece, making it very clear about how different parts of the ice sheet system help sort of control the mass loss and all the different processes and things. So, so I'd be happy to send you the link, but you could probably just Google it. And so we started out with just, you know, putting into context the main sort of driver here for the whole thing is the sea level rise and the increasing amount of mass loss that's coming from Antarctica that's contributing to global sea level rise, but also how all the other elements or sea level rise components are also increasing, but then thinking about the future as well. And this is actually from the paper led by Helen, and looking at the future projections as well and why there is such deep uncertainty. Okay, so this is another paper that came out around about the same time. It's a new journal called the Dialogues of Climate Change. It's a SAGE journal. And we were asked to write this. It's kind of more like a commentary. But this one, we actually put the, to make it a bit different from the science paper, we actually put the pieces of pie in sort of increasing order chronologically. So you can see how all the different components have increased relative to each other. But this really brings out this Antarctic component here, this blue wedge. And so, yeah, looking over onto the right-hand side, the diagrams we put in the SAGE paper, basically looking at where the mass loss is coming from. And one of the speakers this morning said it's all happening around the edges. And I love that because that's going to feed into EDGE, which is what this new mission is that I'm going to tell you about. It's a play on words, EDGE, because it is all happening around the edges. And so, yeah, so basically around the edges, it's kind of messy. And very, this actually here is showing now where all the sea level is locked up in Antarctica. This is sea level potential by basin, so the darker the blue, the more sea level potential. And so this is obviously important, thinking about these different basins and which ones are starting to lose mass to the ocean. So bringing now in the altimetry timeline, why is the talk called Eras of Altimetry? Well, we've actually learned a lot about the ice sheet from many, many different satellite types, but I'm focusing on altimetry for this talk, and I don't want to say that altimetry is the best, but it's the one that I work in the most, and I'm just going to basically focus on that for this talk. But of course, SAR is also very important and useful, and also so is GRACE, and also imagery and worldview and everything. But for the sake of this talk, I want to tell you sort of what we learned from altimetry about the ice sheet and how it's changing. So many of you will have known about this, but basically all sort of started with CSAT coming into the ESA instruments, ERS-1 and 2 radar altimetry, and then coming into ISAT and ISAT-2, the laser altimetry. This is the mission that brought me to the US, and 25 years later, I'm still here. We're also working on ISAT-2. I'm actually the science team lead for ISAT-2. And then in the future, there's a big white gap, which hopefully I'll get time to fill in at the end of this talk, where we hope the white gap will be. This is just a bit of a recap for what we've learned from these missions that you will have heard about, and you will have seen these plots. And I very much apologize for the color scale on these plots, but they weren't mine. These are the original figures from the original authors. So Duncan Wingham used this plot here, and Jays Wally, and then Andy Shepard. The point being here, don't think about really what they're showing, but the main point is they're showing us where the ice sheet is changing, right? And so you can actually start to see, okay, there's some hot spots that are flashing red. Look at me, go in with more detail and work out why. That's kind of what we got from these early altimetry maps that are showing us the hot spots. We're seeing loss. The ice surface is basically going down, which is how you can measure it with the altimetry. The map here of the last one with Andy Shepard, this was actually now going in and looking at the ice shelves and seeing actually the ice shelves are thinning, and that's what's driving the loss on the grounded ice sheet behind. The other thing that you can do with altimetry, which is kind of a second order thing really, it's a bit of an inversion. If you also have radio echo sounding thickness, you can infer basal freezing underneath an ice shelf. So here's a very early, this is over 20 years ago now, almost embarrassing to show it, but a marine ice map under a marine ice shelf that was basically, we got it basically because we had the radar altimetry data and some Russian ice thickness data to help constrain this very difficult to map parameter. Okay, so then along came ISAT and MVSAT, and ISAT was really was like the bee's knees. It was like, okay, this thing's gonna do everything now because it's a laser and it's not gonna have the problems that radar altimetry had, and it's gonna be great. And ISAT was a very exciting, groundbreaking mission. Many of you will have seen this map here. So Hamish Pritchard came to Scripps to work with us on this map and this data. Around 2010 or something, and basically found that where the ice sheets are thinning, which is what we got from these maps here, basically, well, you can sort of see, but the thinning is happening here and here. Where the ice sheets are thinning is also where the ice shelves are thinning. So the ice shelves thinning is actually driving the loss of that grounded ice. And then the other piece of the puzzle here is the ocean temperatures that were put on the same plot. And so where the ocean is warmer is where the ice shelves are thinning. And so the cold water cavities that's where the ice shelves are not changing as much. The warm water cavities over here, where the circumpolar deep water is close, sort of just sitting there on the continental shelf ready, is actually being driven underneath these ice shelves and causing the thinning. This one on the right-hand side is actually using a longer-term record from the ERS altimetry. So this is ERS, and then ERS-2, and then MVSAT. So this is 18 years of change from Fernando Paulo. Many of you will have seen this map as well. And what this could do was actually give us a very long-term, well, it was 2 decades at the time, and you can start to look at some trends and some patterns in there that actually give a clue as to what the driving processes are. One of the things that Fernando was able to pull out from this signal there was actually an ENSO signal in here. There were 2 very strong El Nino events that he could map and look at and see that once you take away the long-term thinning, the ENSO signal was left behind, which was very nice. So the other thing that you can do is you can use the altimetry in combination with knowledge of the dynamics, so the velocity, to back out basal melt rates. So this is kind of the next step. This map actually came out of a meeting from the sea level change team at Scripps many years ago, maybe 10 years ago or so. And I remember Sophie Nowicki saying to me, we need basal melt rates from you. And I said, well, you've got Fernando's map. Can't you just convert that into melt rate, like you know the area? And she said, no, we need melt rates. I said, okay. So Cecile did this really nice paper, and this is basically basal melt rates that go all the way from 2002 all the way to 2018, and really nice for modeling and for using like boundary conditions, but also input for modeling. really nice data set that Sushil was able to produce with that. So the thinning of the ice shelves producing the freshwater meltwater fluxes, and that's what you can get from these data. On the right-hand side is a different way of looking at this, and this time we've actually put everything together on this map. So this is the entire grounded ice sheet and the ice shelves as well, using ISAT-2, which was launched in 2018, and ISAT. So this is about 16 years of change here, this map. It's basically just one epoch minus the other. There's no like temporal variability in here at all. It's just two snapshots difference. But what this shows you, and now there's a different color scale. This is hopefully more intuitive, with the red is the loss and the blue is the gain. So we're seeing this loss around the edges, and also mostly in West Antarctica, in the Amundsen Sea and the Bellingshausen Sea, but also a little bit in this area of Wilkes Land. There's some red sort of hotspots emerging. And what you can see also is that the thinning is happening in the grounded ice, where you're seeing the thinning on the ice shelves. This is the first time that a map actually showed this in one fell swoop, the same data processed in the same way, to show, yeah, there's a cause and effect of the thinning ice shelves and the grounded ice behind it. So this was ISAT and ISAT-2. ISAT now, I sort of look at it like I look back at ISAT, and it's a bit like going back to your flip-top phone. You're like, oh my gosh, how did I deal with that? Well, ISAT was great at the time, but what we've got now is actually better, and what we will get in the future, hopefully, is going to be a lot better. So let me just, I think it was Patrick that said all the changes are happening around the edges. So yeah, in Antarctica, all the changes are happening around the edges, and in Greenland. But let's focus on Antarctica for now. So with ISAT-2 and ISAT, we've had a lot of data in the middle of Antarctica where nothing's happening. And so not to like diminish all the work that's been done in the middle of Antarctica and everything, and you definitely need to know about the surface mass balance and all of that, but for the actual sampling of the margins, the orbit of the ISAT and ISAT-2 instruments were maybe not the best, because the sampling really needs to be around here rather than here, because this, you know, there's just a little bit going on, but not as much. But the other thing about the edges of the ice sheets is that they're really, really rough, and altimetry is not very good at dealing with surfaces like that. It gets really noisy, and so what you end up with is a situation where the bits you need to map are the bits that actually are not very well mapped because the data are very noisy. And so here is the typical sort of, I don't know, weird topography or whatever around the edges. Along a profile. So ISAT-2 is, so ISAT, well, it's going backwards. So basically the big wide one here is radar altimetry. ISAT is, go back. So this is ISAT-2, and then ISAT was a little bit wider. So basically you're getting narrower and narrower and able to really bring out those details into focus. But ISAT-2 still was very sparse track sampling. So we can get very nice details along track, but there's nothing along track. There's nothing around where you're not mapping. So when you're trying to map things like this and this, which is Catherine, where's Catherine? Catherine's beautiful plot that she made for the EDGE proposal of what the edge of an ice shelf looks like. Yeah, the altimetry, it's not surprising, radar altimetry had no luck at resolving any of that, and ISAT-2 is doing a much better job of doing that along the places where it samples. And let me just show you how. So this is actually ISAT versus ISAT-2. This was in the Smith et al. Paper as well. And so you can see this rift. Okay, so the rift has changed a little bit between ISAT and ISAT-2, but the point being, what you can see the most is the resolution of what's inside this rift. In this case, you can actually see melange. You can see a lot more of those side profiles along the edges of the rift, which indicate rift activity. You can actually start to really understand a little bit more about how the ice is deforming as the rifting process evolves. So the ISAT-2 was a real major jump forward, because basically you're going from this single beam flip-top phone thing to kind of like the iPhone, maybe first iPhone, I guess. I call ISAT-2 the first iPhone, and I'm leading up to Edge. I don't know what Edge is going to be. It's like iPhone 32 or something. 40 maybe. Oh, this is what I want. Okay, so these plots actually were the second figure in the science paper. So this is the ISAT-2 the same map that I showed you, the Smith et al. Map, with the red is the thinning and the blue is the thickening. But this also has sea ice on it as well, because you can get sea ice thickness from altimetry as well. So this is from Sarah Kachimi and Ron Kwok, their map. So this is basically the whole of the Antarctic ice, land ice and sea ice together. And then this map was actually redrawn. Like, science wanted to redraw every single figure that we gave them, even Catherine's beautiful figure. They wanted to redraw it. So I guess we let them. So this is the redrawn version. I prefer Catherine's. Catherine's is much nicer. But anyway, they redrew it. And so we've also got sea ice on here as well. And so, yeah, the altimetry is able to detect and map these flows and get some idea of some of the variability around the sea ice pack as well. Okay, the other thing that we ended up putting in there was just thinking about the mass loss processes and their sort of spatial and temporal scales, because when you're thinking about observations, that's the key thing. You need to know at what time scales and space scales do we need to be observing under to resolve these processes and be able to understand them better and essentially maybe hopefully trying to parameterize them and put them into models ultimately. So this is actually borrowed or after a paper that was led by Jeremy Bassis, which was all about iceberg carving, and we put it in here as well. So this is the difference sort of from weeks to decades of carving, so explosive disintegration through to sustained carving, through to rifting and decadal scale carving, and then also melting. So this is basal melting. So this is the normal sort of mode 1, mode 2, mode 3 type of melting, but then thinking about the scales, like the actual cavity scale, but then these other processes that are it's becoming very clear that we need to understand them better, these mesoscale sort of features like eddies and fronts, and then turbulence and convection as well. These are all very small scale. There's no way you're going to pick these up with altimetry, but we need to be able to understand things at that scale to be able to fully monitor them and turn it into models, or parameterize them so you can put them into models. The other figure that we had in the paper was about the grounding zones, because it turns out the grounding zones are really, really key. These sort of edge processes where you know, the ice sheet meets the ice shelf, and this area right here, the basal melt rates are really high, and many things happen at the grounding zone. It's a very important transition for modeling as well, and so very important area for us to study and get right. So that was in there. So I'm just going to jump now through some of the processes that we've learned about using altimetry and some of the reasons why this sort of topographic information, which is a very basic thing, is able to help us resolve and understand processes like this. So have I got 10 minutes? So, yeah. So this is iceberg carving. This is a paper led by Catherine, basically looking at the front of the Amory ice shelf before and after carving. And so you can see this change in the shape of the ice front profiles as before and after the carving event. But you can also see there's a lot of gaps, right? There's a lot of places where ICESat-2 is not able to get data because it just doesn't sample there. Another paper that came out a few years ago by Shuqi Wang, and she's at Penn State. She's done some amazing work looking at rift depth, basically the height of the rift to the freeboard of the rift to the bottom, so this height here, across various ice shelves. This was Amory ice shelf, and she also just had this paper on Thwaites that just came out like maybe 6 weeks ago. And this is a beautiful study, basically using all the data to help us understand these crevasse patterns and which of the crevasses become dominant in iceberg carving and the subsequent behavior of Thwaites. The other thing we're very interested in is what's happening inside the rifts, like this melange inside rifts is very, very, and I'm very interested to hear about the melange talk later on in the week, because it's different. The melange in Greenland is very different to the melange in Antarctica, but the melange in Antarctica is actually possibly responsible for either acting as a wedge or helping to deform the rifts. It's kind of interesting. It's like, is it a glue, like holding it all together, or is it driving it apart? It depends, and we don't know. So we're trying to sort of look at that, and ICESat-2 is able to resolve the thickness of the melange inside the rifts. There's other very key features of ice sheets and ice shelves that we look at, because this is where buttressing is very, very important. So where the ice shelf sits on top of the pinning points is very important to monitor, because as the ice lifts off those pinning points, you can go into a very quick regime change. And so some work has been done looking at rift, sort of changing pinning points, and also interactions of rifts around pinning points as well. This is a paper by Christian Wild using ISAT2 and other imagery as well. And then this one was a very nice paper that Catherine led last year in Nature Geoscience, looking at the Conger Glenser ice shelf over here in East Antarctica. It was just off the edge of Shackleton, and it disintegrated, but very slowly, actually, over decades. But ISAT2 was able to pull out some surface profiles that gave some clues as to how that changed. Okay, I'm going to jump through these. I've got too many things here. Surface melt, another thing, but EDGE can't do that, so I'll jump over it. It's all about the wavelength. So green can look through water, but red can't. And okay, so I wanted to tell you about the grounding lines. So Bryony Freer is a postdoc at Scripps. She's on a Schmidt AI fellowship, and she has been looking at grounding lines with ISAT2. She's been looking at the retreat rates and the tidal retreat of grounding lines, which and it's very nice work. It's actually published, so encourage you to look at that. She found some very large retreat rates in some areas due to the tidal variation. The other thing that she's done, which I thought might be of interest to this group, and it's just in review right now, is she's used this this shape, which she calls the grounding zone viscous bump shape. It's like there's bumps, this feature at the grounding zone, and Christian Schoof wrote about these, and he called them something like wave-like surface feature, I think he called them. Basically, there's this bump at the grounding line, which you can see in ISAT2 topography and also in the REMA DEM, and she's used this to basically map the grounding line from the basal stress transition, but also infer the basal drag and ice viscosity as well, relative, and then also use it to improve the grounding zone thickness and slope estimates, which is really important. So keep an eye out for this. I think it's going to be really nice paper when it gets accepted. The other thing, of course, we've done with ISAT2 is look at subglacial lakes. So hopefully I've got time to tell you about EDGE. Do I still have 5? Okay, perfect. Okay, so just a summary of what we know and what we need. And so look at this circle here. This is ISAT2 over Cook ice shelf. So basically, all of this is just me telling you again, altimetry going back to the 90s has shown us a lot about Antarctica. It's shown us that it's losing mass, mostly from its dynamic margins, the edges. We have a lot of a deep uncertainty because of the lack of understanding, because we haven't really been able to monitor or observe at the relevant scales, the processes that are driving the changes. Satellite altimetry is uniquely giving us this, this topographic signal over the ice sheet to help us understand how it's responding. So we need to continue the record. So this is what we have with ISAT2 over Cook. This is what EDGE is going to do over Cook. Suddenly you can actually see what's there, right? Like you don't really tell what's there with ISAT2. Like it's just really sparse and most of it is white space. But EDGE is going to be able to come in and give you all of the details, and suddenly you see all these crevasses and really important parts of the puzzle that are holding the ice shelf together, but you're not able to map them if you don't have the right information. So we put together this sort of desire, it's like a wish list of time scale of observation required and spatial scale of observation required, all the different things that are on this map here, like shear margins, pinning points, and don't, like, I know that we agonized for weeks over, well, months actually, in fact, was it years? 3.5, over what exactly are the end and start scales of all of these things, but essentially this is about right. And so what it's trying to do is show you that ISAT2 can sort of get some of this, but EDGE is going to be able to get you right into this area here, this observation of all of these features that you can't get with ISAT and the current state of the art. So what is EDGE? Okay, so EDGE is hopefully going to start a new era. Very excited about this, which is kind of amazing after 3.5 years that I'm still excited. But it's been a lot. It's been a big slog. We just submitted the concept study report on June 12th. It's one of 4 missions that are in the NASA Earth System Explorer competition. And the other one that you may have heard about is called Odyssey from JPL, also with the Scripps PI. So Sarah Gilly and I have been very closely aligned. So this is the front cover of our proposal. I'll talk to you more about what these are, what the ground tracks are in a sec. It's in collaboration with Goddard Space Flight Center. So Brian Blair is the deputy PI for the instrument. He built the instrument Elvis and also Jedi instrument. And then Scott Lusky, who many of you will know, and John Armston, who's the deputy PI for ecosystems, because this is not just for ice, it's also for ecosystems. Turns out I love trees. Kind of got really into them. So this is the coverage of ISAT-2. This is about 5-7% mostly for ISAT-2 over the Antarctic for the land ice and the sea ice. This is the coverage for EDGE, 60-70% after 2 years. So we're going to have much better coverage. And these are the orbits. So Jedi is in green because it's on the space station. It can't go, okay, 5 minutes, perfect. EDGE is the gold, because gold, standard, you know, we use that color. ISAT-2 is here. So what you can see here is, okay, there's a hole at the pole, but you're not actually missing much. And, okay, we are missing subglacial Lake Engelhart, so that's a bummer. But for mostly what we are getting is all of this change around the edges, around the margins, and the same in Greenland. We get all of Greenland as well. And, you know, there's a few bits we won't get, but you should focus on what we do get. And so what this does, it's a sun-synchronous orbit, which turns out is a lot cheaper. It turns out there's not much money for these missions, even before all of this nonsense. There wasn't much. And so we're kind of like trying to get everything into this mission. So the ecosystems and ICE group work really well together on this mission. It's been fantastic, actually. This is, we're going to be able to have targeting, because it's a Maxar Legion spacecraft, which is the same one that they use for Worldview, and it can target. So you tell me you want to go to, I don't know, Helheim Glacier or something like that, then we can actually target that and get it more often if we want. We don't know what we're going to want in 2030, but we framed the whole thing around tipping points, and I put this slide in actually just today because we were talking earlier about the sort of more global system, but all the different things that we get, it's not just land ice and sea ice and vegetation, it's also permafrost, it's also the snow. We also get snow water equivalent as well, the snow depth part of that. So it's actually going to be a lot of things in one. The mission is going to have 5 lasers with 8 beams each, so that's 40 beams. And so it's basically going to do this. So I already showed you the ISAT-2 to EDGE transformation. This is the Jedi to EDGE transformation. If you're interested in the ecosystems, it's amazing. It gets the canopy as well. Here it is over the ice. They're called mini swaths, and so what they're basically doing is they're imaging the ground. So you've gone from having kind of like strips of wool or something to now ribbons, right, around the Earth, and you're going to get a lot of information from that, a lot more than we've currently got. This, I've never shown these in an audience before. We've been told we can do this because we want to promote the instrument and get people excited. This is what it'll look like over basal channels. This is an evolving basal channel that was completely missed with ISAT-2. Well, not completely missed, but only partially seen. This is a rift example that Catherine worked on with Laurie Padman, and basically showing us what we're going to get over the fronts of these ice shelves that are carving. This is what we have with ISAT-2, and the edge is so good you can barely even see the ground tracks there. And this is what we're going to get over a propagating rift. Okay. And so essentially what we're doing is we're kind of increasing our, this is the eras, right? This is where we were with ISAT. We've got these sparse measurements. We're going up. This is our iPhone 1. This is our iPhone, I don't know, 6. I've lost track of where we are. But up here is the future. In the end, what we want is gap-free monitoring, but EDGE is going to get us there in this sort of short-term way. It's only a 2-year mission because of the funding, but we're going to have a very good understanding of the surface topography of the Earth after that. So hopefully we're moving towards this kind of thing in the future, but EDGE will kind of fill in that gap because there will be a gap. And it's also the only thing that we have in the pipeline for altimetry in the future. So hopefully the Eras of Satellite Altimetry will be CSAT all the way to EDGE at some point, but we will see. I don't know if I've got time for geoengineering, but I wanted to just throw this up. Do I have 1 minute? I just wanted to just quickly end on this because I wanted to say in the science paper, actually nobody, not a single reviewer, not the editor, and no one has commented on the fact that we had a whole, don't try and read this, but we had a whole 2 paragraphs in there on ice intervention because Rob DeConto had asked for that when he asked for this paper to be written. And so this was sort of the biggest thing that we came away with. Nobody's commented on what we wrote there. We spent a lot of time agonizing over what to write. But I also wanted to point you to this paper, which is coming out soon. You can actually download it. It's a preprint. But Martin Siegert led a group of us basically on going through all the different geoengineering ideas that have been put forward and saying, you know, our thoughts on those. So that's coming out in September. But just wanted to throw that out there as the final thing. So, okay, thanks.
Thank you very much, Helen. And maybe that's something we had discussion on Thursday afternoon. Maybe these are some ideas we could talk about on Thursday. Questions for Helen? Yes, Henry.
Thanks. You showed a plot at some point of ice thickness from laser altimetry, sea ice thickness. Could you talk a bit more about that? Is that like seeing the leads through the sea ice flows?
So that's how, Ellen's, now I'm going to probably get it wrong, but that's how you get ice thickness from altimetry. You need to map the leads, which you probably know, right? You need to get the open ocean in the middle, and then you get the freeboard, and you turn that into the thickness. So that's the challenge, actually, is detecting the leads. We've done a lot of work on the EDGE sort of concept study on how well we're going to be able to detect those leads. The fact that we've got such a great across-track sampling is really good for that, because you're going to pick up leads all across that full swath. But yeah, if you can't detect the leads, it's very difficult to get sea ice thickness, because otherwise you need the geoid very accurately. Right, because you need that control to the mean sea surface, because you haven't got the geoid's only good to what, 0.5 meter or something, and so that translates to a large thickness error. So I don't know, did I get that right, Ellen?
Thanks.
Yes, Eric, just behind you.
Thanks, Helen, for that really great talk. It's nice to be reminded of how we know some of the things that we now take for granted. My question is simple. You said that the EDGE program, if it's funded, it's just a 2-year mission.
Yes.
In the event that things return to some sort of normalcy and more funding can happen, could it go longer, or yeah?
Yes. So
okay.
yes, it has. So and let me just touch. So something else that you said, didn't quite ask this, but so the budget has been fixed since the decadal survey. Actually fixed to the point that it hasn't even increased with inflation, which is kind of annoying. We're working with $310 million for these missions. And we were supposed to be working towards 2 of them. Like this AO, 4 in step, in phase A, we're working towards 2. The latest presidential budget request that came through said only 1 will get funded. But that doesn't take away from the fact that if EDGE goes, we'll have this amount of money to spend on it. If it's up there, it has enough fuel on board for 5 or 6 years, and we've worked out that I can't remember the exact number, but it's actually not that much to extend it for a year. So we're hoping that people will understand the value of it to the point that we can actually get donor funds, or I don't know, some other funds to keep it going. So
are measurements still being made, but no one's collecting them if there's no money? What actually happens?
Yeah, I mean, that's the thing. Well, you basically, you're not going to turn off the instrument. It'll still be going. But yeah, right now we're only funded for that 2-year period. So,
thanks.
Yeah. And it was quite hard to, in the end you had to come up with a proposal that was good enough and robust enough to fit that 2-year sort of mandate. And even 1 more year would have been a lot easier for ice chain, for example. But in the end, yeah, 2 years is what we had, so.
Thank you. And I was wondering if you could comment on there's another mission that seems planned after 2030, and I was wondering if you knew about this, like, what is it, Rose L or something?
Oh yeah, that's an ESA. That's an ESA mission. Yeah, these are all the ones that we know about. So Crystal is the next sort of radar altimetry. So the radar altimetry ones are all in the sort of brown color. Crystal is meant to be launched. Well, I don't know. Crystal was mentioned in the PBR as well. I think it's going to be launched around 2028, 2029. We don't exactly know. So yeah, so hopefully Edge and Crystal will be flying together, which would be great because you have a radar and a laser. So the radar and the lasers complement each other really well because radar altimetry penetrates a little bit into the snow surface, and so there's that uncertainty, whereas the laser bounces off the top mostly. So there's that, and that's good for sea ice too, right? Because you can get the snow, well, that's the idea. You can get the snow depth on the sea ice. But there's pros and cons. So the big thing about altimetry, laser altimetry, is the clouds, because at that frequency, clouds get in the way. Whereas radar are great because they see through the clouds, not very technical, but wider footprint. So you know it's trades. Everything with remote sensing is a trade. So yeah.
Absolutely. Thanks. Other questions for Helen? Yes, Andy.
Thanks for the nice talk, Helen. We have been looking at the ISAT-2 data to try to understand whether you can help better understand ocean boundary currents around Antarctic.
Yeah.
I was curious, was there an ocean component to the EDGE proposal in terms of what you can do for SSH?
So there wasn't, but it doesn't mean that there won't be. So in a 15-page proposal, we actually already split vegetation and ice down the middle, which was really hard. And every time we said, oh, we could do permafrost, oh, we could do ocean, oh, we could do this, Goddard would just be like, you can't keep watering it down. Like, yes, of course, but you need to have something that gets the mission funded, and then you add everything on. We actually had a science enhancement option. We didn't have ocean in there yet, but we could. Because we will collect a lot of really good data over the ocean. And one of the things I talked about a little bit with Sarah, actually, is we're going to be, the two missions together in the marginal ice zone would be transformational. Like what we can do in the marginal ice zone with EDGE in terms of getting wave spectra and things is incredible. And Odyssey as well, to get the currents and the winds. I mean, it really would be, that's where those two missions converge, and it's a game changer if you got them both. But, you know, right now there's only going to be one funded, so we're kind of back to competing. We've gone from this, oh, we're going to get them both, to, oh, okay, yeah, this is all happening like the last month, so, or whenever. But yeah, for the oceanography, it's going to be amazing. And you've already, as you've seen with the ISAT-2 data, you're getting little snippets of what you might see, but imagine that along a mini swath. Yeah.
Thanks. Yes, Till.
Hi, Helen. Great talk, thank you. I wanted to ask a little more detail about the targeting and whether there's a trade-off with extra fuel consumption and how much you're thinking about targeting versus standard orbit. Thank you.
Yeah, I'm glad you asked about that. So targeting is quite an innovative, well, I mean, we have done targets of opportunity with ISAT-2, but this is more, we're actually going to go to Helheim Glacier, and then we're going to spend more time there and collect more data. We call it dwelling. It's actually one of our measurement acquisition modes. And so now you fill in even more. Like, it's already fantastic, but it's going to be like a complete, like you've flown a plane over it with LiDAR kind of thing. It's not going to take away from the fuel, but it is going to take tracks away from other things. So one of the things we do have, though, and this takes away from the ocean side of things, which we haven't played up in the proposal, we have this thing called repeat track densification, where you sort of borrow tracks from the ocean and move them all together over the coast. So you get very nice sampling of like shorelines and like for sea level rise stuff, mangroves, tidal flats, you know, estuaries, that kind of thing. That's a really cool application. But also for the edges of ice sheets, we could do it too. Although you're going to take away from the sea ice. So, yeah. But targeting is going to be great. And we want it to be a community mission. So we want, it's not like this is our mission, we're doing what we say. This is a mission we're hopefully going to get, and people are going to say, right, this is going to be an important target, we need it to be in your list. So. The period, it's 91 days. But yeah, but they don't repeat. They don't need to repeat because there's so many tracks. It's just like a swath mapping thing. So it's only a near repeat. So, but it comes back to more or less the same place every 91 days. But with the targeting, you can actually come back. I think it's once a month you can come back with the targeting. So if there's something like very important that's happening, you can actually come back and sample it more often.
It's still time limited, so the shortest would be a month.
Right. Yeah. Yeah, and it's sun synchronous, so it goes from 82, more or less, north and south. So there's that big hole at the pole, but as you've heard, that doesn't matter.
I think, Benji, you had a question?
Yeah, sorry.
This looks very cool, and I definitely hope it gets funded. So I don't want this to come off as like a pessimistic or cynical question. It's a curious question. I was not involved in the field when this was all happening, but my vague understanding of ISAT-2 is that it was like, it took a significant amount more money than was initially sort of assigned for the project to debug all the laser equipment, get everything up and running, and then if you add in the operational like costs that eventually took, like as it's actually been being used and data being published, the actual cost ends up being like maybe almost twice the amount of the initial budget, which is already significantly more than is being sort of on the table for EDGE.
$1.1 billion was ISAT-2.
Right. Compared to maybe a $560 million initial estimate.
Yes.
So what happens to a project like this? Obviously, if you get more money, like, or if there's some flexibility in future funding, which is always uncertain, but given the sort of scenario that we're all in right now, like how do you approach a project that has so much more potential, but also so much kind of untested technology, and what is the sort of thought process around that for you?
So that's a great question, and I've been fighting that one for 3.5 years with Goddard because of the ISAT-2 overrun. JEDI, however, which is what this instrument is based on, was delivered on cost and on schedule, and that's the path we're on.
Absolutely. Yeah, no. We need to be optimistic and get this going.
As diplomatic as I could be. So, yeah. So it is tested technology because it's already flying on the International Space Station. It's just going to have more beams. So, yeah, it can't overrun because there won't be any more money. And we've had to show we've got margin. We've got 27% margin in our budget. So, yeah, we cannot go over. And, yeah, it's been hard to convince people of that, but the numbers add up, so.
Is that different than Atlas, the amount of testing is sort of that fact that it's already running?
Yeah, well, Atlas was a whole new instrument that hadn't flown before, whereas JEDI is based on Elvis, which has flown for years and follows on the, EDGE builds on Elvis JEDI, yeah. So CRL 7, if you're interested, technical readiness level.
Maybe we have time for one last question for Helen.
Yeah, so just a quick question. Can you talk a little bit more about the technology and like the wavelength, the swath width of the mini swaths?
Of EDGE?
Yeah.
Yes. So I guess here, this is the only one that shows how it works. So it's full waveform, 1064 nanometers, so it's red laser, just like ISAT was. It's not green, which is why it can't see through water. So it doesn't do the bathymetry that ISAT-2 does is amazing, but EDGE can't do that. It's really the only thing it can't do, because it is this red laser, near infrared laser. So it's waveform, it measures a waveform. It's basically, well, but for everyone else, it's basically just recording a waveform from the surface and measuring the time delay to that waveform, right? Output pulse, input pulse, and turning that into a height very accurately, and then with the knowledge of all the other things, the other corrections, get a very accurate measurement on the ground of what the surface height is. The mini swaths, it should say on there, but actually it doesn't. I just realized They are, so each, it's 60 meters wide, and there's 8 of them. So they're 120 meter mini swaths, basically. No, 15 meters, sorry. 15 meters times 8. So it's 120 meters wide, each of these mini swaths. And there's 5 of them. So this is 120 meters wide. And they're 1.2 kilometers apart. Okay. Sorry. So it's like that kind of thing. I always draw it like that. So they're 1.2 kilometers between, and then 120 meters swaths. Yeah.
Thank you.
Oh, one more.
Okay, maybe less, very quick.
Why change the red from green?
Well, in a way, why did we change from red to green? Yeah, I mean, when I showed this mission to Bernard Minster, he's like, oh, you're going back to waveforms. I mean, it's kind of not really, because Jedi never wavered. We're just going with the Jedi path. There's like 2 paths from ISAT, Jedi and ISAT-2, and we're going with that one. So.
Thank you. Let's thank Helen again. Great.